So we're done with chapter 4, and this is kind of exciting because that means we're done talking about derivatives for now. We're actually going to come back and talk about derivatives at the very end of this class, just as a kind of a, oh hey, by the way, also this other thing for the derivatives. But we're going to come back to that later. I wonder what new and exciting topic that we're going to talk about. I'm sure it's completely unrelated to derivatives, and oh, hey guys, we're talking about antiderivatives and indefinite integrals here. And I think by the name antiderivative, you can probably guess what we're going to be doing here. So the way I sort of think about antiderivatives and indefinite integrals, we've learned derivatives. We've seen the addition of calculus. Antiderivatives is now the subtraction. It sort of goes backwards. So if I start with a function f, I take its derivative, I would have f prime. We're going to see now if we can go backwards and work our way backwards to f using antiderivatives. These two words as well, antiderivatives and indefinite integrals, these two terms, are essentially interchangeable. They basically mean the same thing. I will use them interchangeably, so if I say antiderivative, I'm also talking about indefinite integrals and vice versa. So the way we represent antiderivatives and indefinite integrals, we use this kind of funny squiggly line right here. This is the integral. This says the integral of f of x dx represents the indefinite integral or the antiderivative of f of x. Like we said over here with our chart, this is the opposite process of taking the derivative. It turns out that antiderivatives are much more complicated than derivatives. It turns out it's a much more difficult process. But we're going to focus on some relatively simple ones. We're not going to do too much with antiderivatives. And then the dx right here, so you'll notice I have the integral of f of x dx. This dx right here just tells us that we're integrating with respect to the variable x. It does have some deeper meaning, but for now, I would just say, right now, it just kind of lets you know, okay, we're using the variable x, which is particularly helpful later on. If you were to take, say, like a calculus 2, we might have double integrals, in which case we might integrate some function with respect to x and then with respect to y. We're only going to look at single integrals in our class, but just so you know, there are other things out there. And then this part right here, you always add c when finding the indefinite integral. I want to talk about that in just a second here. So we're going to see if we can look at a few examples and kind of think about it, and then we'll talk about maybe some shortcuts. So first, I would like to find the antiderivative or the indefinite integral of 3x squared dx. So here's what I'm thinking. I'm thinking, okay, my derivative, f prime of x, is really 3x squared. So I need to come up with a function f of x that gives me that derivative. So I need a function that when I take its derivative, I end up with 3x squared. So okay, if you think about the derivative, like taking the derivative as a process, and here we want to talk about f of x. If we think about taking the derivative as a process, what were the two steps that we took? For derivatives, we did two things. First, we multiplied by the power. And then what did we do? We subtracted 1 from the power. These are the two steps we did for the derivative. So if I want to try and come up with an f of x here, you might say, okay, well, if these are the steps for the derivative, why don't we just do the opposite? Let's start with dividing by the power. So if I divide by the power, and let me do this in a different color here. If I divide by the power, I would have 3 divided by 2 times x. And then let's see, instead of subtracting 1 from the power, I would add 1 to the power. So 3/2 x to the third. And let's check our work. For all of these, we should be able to check our work. So if I take the derivative here of this function that I've just found, I would multiply by the power, so 3 times 3/2, I would have 9/2 times x squared. Well, shoot, this is a problem, because my derivative doesn't match what I started with. I should be able to find an antiderivative and then check my answer by taking the derivative. I should end up in exactly the same place that I started. So something's wrong here. Something with just switching or doing the opposite of these steps, that's not going to work. So the key to these is we're not just going to switch the steps. We're not just going to do the opposite of these two steps. We need to also reverse the order that we do these in. So when we talk about antiderivatives, and you can probably peek at the formula down there, but for antiderivatives, instead of starting with multiplication or division, we're actually going to start with the power. We're going to, rather than subtract 1 from the power, we are going to add 1 to the power. And then in step 2, instead of multiplying by the power, we want to do the opposite. We are going to divide by the new power, whatever our new power is. So okay, here's our derivative. F prime is 3x squared. So when I go to find f of x then, my function f of x, I'm going to add 1 to the power. I should have 3x raised to the third power. Divide that by 3, and I have x to the third. So let's just double check our work here. Let me do this in a different color. How about I do this in purple? If I check my work, if I take the derivative of x cubed, do I get 3x squared? And actually, I don't, it's not really a whole lot of work to show here. But yeah, if I take the derivative of x cubed, I would get 3x squared. So that means that if I'm evaluating, let me just section this off to the side. If I'm evaluating the indefinite integral of 3x squared dx, I would say that's x cubed. But we have a slight other problem here. It's that this is not the only function whose derivative is 3x squared. I could come up with infinitely many more. What if I said x cubed plus 1? The derivative of this function is 3x squared. What if I said x cubed plus 2? Derivative of that function is 3x squared. Or x cubed minus 4. Derivative of that function is 3x squared. So we have this problem, this slight problem, where we don't really know what the constant should be. And without more information, we actually can't know what that constant is. If I had just a little bit more information, if you told me one single point on my graph, I could go and find that constant. But without that information, I don't know what that constant is. And this is why we have to always add this c when finding the indefinite integral. So this is why we always have to add plus c on every single one of these problems. So our antiderivative should be x cubed plus c. Here is our solution, x cubed plus c. That is our indefinite integral. So for right now, for every single one of these problems, after you find an antiderivative, you need to add plus c. Every single time. That c has a special name. It's called the constant of integration. And myself and other calculus teachers take great pleasure in looking at and taking like a point off on every single problem that you forget plus c on, because it is just that important. So make sure that you don't forget that plus c every single time in every single one of these problems. So let's look at another. Next up, I have the indefinite integral of 8x dx. So here we said, okay, here are the steps down here. We want to add 1 to the power and divide by the power. Add 1 to the power, divide by the new power. So this is really 8x to the first power. I'm going to add 1 to the power. This is really 8x squared divided by my new power of 2. And then, of course, I have to add my constant of integration, so I have to add plus c. At this point, I am going to simplify this. 8x squared over 2. We can clean that up just a little bit and say that that is 4x squared plus c. If you just want to jump straight to this last answer, that's perfectly fine with me. But if you need to take that intermediate step of actually showing, okay, this is the new power, I'm going to divide by that new power, then absolutely, go right ahead. The next couple are a little bit trickier. First, I want the antiderivative of e to the x dx. And for this, I need to think about, okay, essentially I'm giving you a derivative again. So we say, okay, f prime of x is e to the x. I need a function whose derivative, when I take its derivative, I get back e to the x. Well, you would tell me, but of course it must be e to the x. And of course we have to add, yes, our constant of integration. See, so we see this relationship happen once again. If I want to evaluate the indefinite integral of e to the x dx, this is equal to e to the x plus c. So this is my indefinite integral here. Again, you should be able to check your work on every single one of these. If you're not sure, take your derivative. Take the derivative of e to the x plus c. Derivative of e to the x is e to the x. Derivative of c is 0. Go back and do some of the other ones. Derivative of 4x squared. If I take the derivative of 4x squared, I should end up with 8x. Derivative of x cubed, that gives me 3x squared. So on every single one of these, you should be able to check your work. Next, I want to find the indefinite integral of 1 over x dx. This one's a little bit tricky. If I'm looking at that problem, I say, this one, you're trying to trick me, Mr. Huber, but I'm too smart. I'm going to rewrite this with a negative exponent, so x to the minus 1 dx, and then I'll say, okay, I got to do these two steps, right? I've got to add 1 to the power, and then I've got to divide by that power. So I add 1 to the power, I have x to the 0, divided by my new power of, dividing by 0. It's not going to work here. We can't use our general power rule here. 1 over x is kind of a special case. So we need to think about it, kind of just take a step back here. Essentially, I'm telling you, hey, f prime of x, that's 1 over x. So give me a function whose derivative is 1 over x. And you would tell me that antiderivative is natural log of x, right? If I take the derivative of natural log of x, I would end up with 1 over x. There is one small difference here other than the plus c, which, yes, we should have the plus c. We should say natural log of absolute value of x, and that's just taking care of our domain. If there's a problem where you forget to put the absolute value, I honestly don't know if my math lab will mark it wrong, but I'm going to be looking at your work anyway. And to me, if you leave off the absolute value, it's not a big deal. I'm not going to worry too much about it, but it really should be there. So when I find my antiderivative or my indefinite integral, I should have the natural log of absolute value of x plus c. Again, if you're unsure, if you want to check your answer, take the derivative. The derivative of natural log of x is 1 over x. So this is my solution. A couple other minor things that I want to point out here. And that is, and actually let's just erase this, I want to rewrite it anyway. If we take the antiderivative of 3x squared dx, we said that was x cubed plus c. So notice a few things here when I find my antiderivative or my indefinite integral here. After we either use our power rule or we identify the indefinite integral, notice in every single one of these problems, two things happen. Along with the function itself changing, so we add 1 to the power and divide by the power, notice that this integral symbol, it drops off, it goes away. So after you find your antiderivative over here, you're not going to write this squiggly integral symbol on that right-hand side. It's gone. This is really a piece of instruction. It's telling you to find the antiderivative. The other piece that goes away here is this dx. That dx, remember, is just telling you to integrate with respect to x. It tells you that x is the variable that we're integrating with here. So that also disappears in our next step in every single one of these problems. I don't have an integral symbol, I don't have a dx. No integral symbol, no dx. No integral symbol, no dx. So after I find my antiderivative, we're going to drop that integral and drop the dx. This is something that I just see students make this mistake all the time, and it's not a huge deal. I mean, I think it's kind of a big deal, but in the grand scheme of things, you are still, doing the correct process. It's just a matter of notation, which I think actually is kind of a big deal in the long run. But these 3 or 4 examples here kind of set up our general formulas for indefinite integrals. When we look at indefinite integrals, they're going to fall, at least for right now, they're going to fall into one of 3 cases here. So we have the indefinite integral of x to the n dx. So in that case, we add 1 to the power, we divide by that power. So that's our general power rule for antiderivatives, for indefinite integrals. Adding 1 to the power, dividing by that power. And notice in every single one of these, we're going to have that plus c, that constant of integration. If I'm integrating e to the x, well, it kind of behaves just like its derivative. The antiderivative of e to the x is just e to the x, and of course plus my constant of integration c. And then as we saw in the last example, if I want to take the antiderivative of 1 over x, that would give me natural log of absolute value of x plus c. So these are the 3 for right now that I think you have to know and you have to memorize. We're going to look at a bunch of examples in the next video and just hopefully get a lot of practice with these 3 skills. So these 3, yes, I think that these 3 are absolutely worth memorizing. We're going to be using them a lot. All of the examples that we look at in this section will essentially boil down to one of these 3 cases. One other thing I'd like to talk about before I wrap this video up here, just a couple of properties of indefinite integrals that I want to make note of. The first is if you have a constant multiple of k, you can kind of take that constant multiple of k and factor that out. So notice in the next step, I've pulled that outside of my integral. So as long as it is a constant, now it has to be a constant. You cannot factor out a function of x. So you can't factor out, say, a natural log of x or a power of x. It has to be a constant. So we'll see this a lot in the next section. If you want to simplify your integrals, you can just take some of those constant multiples and pull those out until we get a little bit more comfortable with integration overall. The second is that integration will quote-unquote distribute over addition and subtraction, not over multiplication. So if I want to, I can sort of take this one single integral. Here I'm integrating f of x plus or minus g of x dx, and I split that up. I can say, well, that's the integral of f of x dx plus or minus the integral of g of x dx. I'm sort of taking this integral and sort of applying it to each function separately. Again, the thing I'll note here is that it will distribute over addition and subtraction. It will not distribute over multiplication. Multiplication and division are going to be a little bit more tricky, just like they were with derivatives. So we're going to have to talk about other rules for finding antiderivatives if we have multiplication or division in our functions. So these are two that we're going to be using a lot in the next video, and these hopefully shouldn't come as a huge surprise because we actually saw these two properties for derivatives as well. So I think it sort of makes sense that they're making the jump to antiderivatives here as well. So take a look at the next video if you're still feeling a little bit unsure. We're going to look through a bunch of different examples of indefinite integrals and see if we can't wrap our heads around this a little bit more.